everybody. So today we will be talking about RAID. So we will be covering main aspects of the RAID, main building blocks of RAID, task, actor, objects, and how we deploy clusters on RAID. So, but before going to that part, let us understand what is RAID. RAID is an end-to-end solution which allows you to scale your machine learning and Python applications. RAID has a lot of useful tools integrated within it, both for low-level application scaling, such as cluster configuration, auto-scaling configuration, etc., etc. They have a lot of templates for deploying on most famous cloud service providers, such as AWS, Azure, etc. Of course, they also have tools for deploying RAID applications on your on-premise infrastructure and also on Kubernetes, which is kind of the most famous one at this moment. On the next level, they have already the programming language interfaces that they provide for scaling of your applications, so such as tasks and actors that we will be covering pretty soon. And the top level, as the RAID kind of mainly focuses on scaling machine learning models, serving large-scale machine learning models, and also training them. They provide this RAID AI runtime, which is new. They have just added this into under one umbrella, but they allow you to prepare training data, tuning your models, scoring and serving on a very large scales in a distributed manner. So if you are a data scientist, you may use RAID to scale your single workload, such as like feature extraction, audio, creating image features, audio features, or doing large-scale computations of data sets, or you can serve your ML models in a very in a production environment in a very scalable manner. If you are an ML engineer, you can utilize RAID to have use RAID as a unified interface for all your infrastructure manipulations and all your auto-scaling and distributed computations. So the first part of the main objects of RAID is task. Are tasks. So a task is a kind of asynchronous function that you register by asynchronous. You will see pretty soon. So basically, to create a task, you wrap your Python function with a RAID remote decorator. And the main difference between the standard Python function and task is that you call a task via RAID remote function, not directly. You don't call f directly, but you call f.remote. Here we have function that kind of is not that interesting. It just sleeps for 5 seconds. But we call this function 5 times. And what we see that the total execution time is actually not around 25 seconds, but it's just 5 seconds. It is because each task execution is done on a separate worker. So RAID has these workers which are kind of Python processes, but on steroids. They have a lot of stuff integrated within them, which helps RAID to synchronize those processes and allow easily transfer data between them. But we basically get a parallel running function because just adding this RAID remote decorator bit. And like if you want to pass arguments, we will see also shortly, you pass those arguments into array remote. You have your ordinary Python function, and then you pass your argument in a remote call. The next good thing about Ray is that it allows you to specify resource requirements for tasks. You can basically say that you need, for example, for running this f function, you need one CPU core, and this will help Ray during its scheduling process, because Ray is a distributed system. It has to kind of schedule the task on in a multi-node environment. So for that, it should understand what are the resource requirements and what resources are available. You can help Ray do that by basically specifying these resources. Here we have a function for which we specify one CPU as a requirement, and in the body of function we get that requirement. We set our num threads environment variable, which controls the number of threads that NumPy allocates for each of its operations. So basically we say, you may use only number of CPU threads for doing your computations. And then we basically do the same as before. We call f.remote. So this is called resource. So we are specifying resources during the declaration of function, but we can do also at runtime. So basically we do f.up options and then specify the number of CPUs. So for example, in this case, and we have for one call of this function, we may have 2 CPUs as a requirement, and for another one, we can have 3 CPUs as a requirement. So we can request those resources dynamically. But please note that this doesn't mean that. So Ray doesn't limit the resources that your task allocates. So if you, for example, specify that you need 1 CPU and then use hundreds of CPUs, an application fails, it's your fault. The only thing that Ray is responsible for is to find node within a cluster that has the specified resources available. The case is a little bit different for GPUs, because if you specify the number of GPUs, Ray sets the fully visible devices environment variable, which kind of limits the number of GPUs that your process will see. By doing so, it kind of makes sure that tens of PyTorch applications tasks that you have do not use more than the specified number of GPUs. And as I said, those resource specification is very useful for allocating space and scheduling the task. So scheduling is kind of process when Ray finds a free space in your cluster and then assigns your submitted task to that node. And for that, it has different heuristics. So the one basic one is kind of find the first available node. So a node is available if it has the specified resources, and those resources are free, so they are not occupied. So a node is feasible if it has those resources, but they are allocated. It's infeasible if they are not. So the node doesn't have those resources. And if there are no available nodes, it will wait for sometimes if there are no available nodes, but some of them are feasible, Ray will try to wait for some specified time for a feasible node to become available. And by default, Ray tries to pack a lot of tasks into a single node because so there are like those data transfer overheads that you should take into account, because if you kind of spread all your tasks across different nodes, and those tasks communicate a lot with each other, so one depends on the other's outcome. Maybe they have a pipe with which they communicate, and those like ray pipes or ray queue, and those tasks are different nodes, so you kind of communicating a lot of data between different nodes. So by default, it tries to pack those tasks into a single node to reduce this overhead. And if it's not already possible, if the node is overloaded, it creates and spreads all those tasks. And you can also specify the default strategy as spread if you are sure that there are like little or no communication going on between tasks. And there's also a fully manual method of specifying the node for scheduling. You basically say that I want this task to be scheduled on the specified node. So you specify node ID via this node affinity scheduling, and the task then gets scheduled on that specified node. I think I'll stop for. Actually, we will have reserve last 5 minutes for the question. So I'll continue on that. We will do Q&A after this. The next core component of Ray is actor. So tasks are kind of stateless. If you see the functions, and it is recommended. So tasks were Python functions, and it is kind of recommended to have them stateless, to not depend on a global state, because there are some considerations on that. But actors are different. They are stateful. And an actor is basically a Pythonic class wrapped with Ray remote. So we have an ordinary class A here, which has a counter initialized by the initial value, increment, and get counter. So we create an object, or just basically we create an actor by by the same way that we create task by dot remote, and then specify arguments for the initialization. What we may see here is that methods on the same actor, so on this object A actor, we call 5 times increment. So increment function is called 5 times, and the execution time is 5 seconds. It is not that those increment methods are called already in parallel, but that they are called sequentially. So methods for an actor are called sequentially, and Ray basically an actor object has a queue, and Ray queues this function calls, and it guarantees that those methods are called in order. And here we kind of get the counter result. But methods for different actors are, of course, called asynchronously. They are called in parallel. So here we have the object A actor of type A and object B actor of type A also. And we increment the counter of object A actor 5 times, and same for object B. And please remember that we have this times flip here, which means that if those methods were run in sequential manner, we would have here 10 seconds, but we have 5 seconds because only methods for object A are run in sequence and only object B's method are run in sequence, but those sequences are run in parallel. So you have two parallel sequences, 6 operations running. But to overcome this, Ray also supports asynchronous actors. So you basically may have an actor that has an asynchronous method defined. It's not different than standard async functionality. You can even await an asynchronous method of an actor here, which kind of crosses the gap. So it kind of provides consistent interface between Ray and async here. The good part is also you can do this Ray gets that we keep doing, which gets the result. So you can either go with your async interface or you can go with Ray interface. And here we do 5 times increment example, and we see that it doesn't take 5 seconds. It takes less than 5 seconds. It's not ideally 1 second, but we have 1.46 seconds, and for sure we like incrementing 0.5 times we get the value of counter 5. So these async actors allow us to execute actor methods asynchronously, so kind of overcoming that sequential manner by default. That is the default setup for actors method execution. But there's also another option, the threaded actors. If you kind of have heavy computations in your actors, the await is not going to help you a lot because execution will come to that heavy computational part. It won't await, it will occupy the CPU resource, and the other threads, other methods will start because they won't have the resource available. So for that, Ray supports these threaded actors, and to basically have a threaded actor, you should specify the number of concurrents, the max concurrency parameter that basically tells how many threads to allocate for this actor. And as before, you can specify it either during the declaration or dynamically by the .option method. And here the one important thing is that you may not have asynchronous function in a threaded actor. So here we have an example of 2 threaded actors. We call this is one function that kind of checks its initial value 1, and we have the increment. And kind of so if you have a guess what is the output for this, like what is the order, what we will be getting for this, you may think on this as an exercise, but the issue here is that it is kind of undefined because when we call those methods in this way, we have no guarantee which one will be executed firstly, which one will start execution firstly. And sometimes you will get that this is true, sometimes you will get that this is false, depending which one is executed firstly. If the increment is executed firstly and then this one is executed, then you will get true. But if this one is executed firstly, then you will get false. And this is kind of an undefined behavior, so you must be a little bit careful. Compared to standard Python, when you use threads in Python, you join them. So the order of joins, the order of start and joins kind of specify which thread starts the execution firstly. But if you are going to batch them in a array yet, then you kind of don't have that guaranteed control here. And please be aware that Ray doesn't remove global interpreter lock, so you kind of have kill within threaded actors. So it's not like kill-free environment. And the one of most useful things of actors is they can be fault tolerant. So it may happen that your actor dies. So because actors are kind of workers, and it may happen that they die, or maybe an exception. Your method runs an exception, and stuff like that. Here we have actor which increments method as a little bit of suicide code there. And what it does here, so if initial value is equal, it gets to 10, then we just exit this worker. So as this code is run on a separate worker, this basically kind of kills that worker. So whenever the initial value gets to 10, we kill the worker that runs this actor. So basically we kill that actor. And you may imagine that this is an artificial example, but you may have cases like this that it runs. There's an exception, or maybe something like you have a bug or something that happened within your actor.
But sorry for interrupting. The time is over there. Maybe one more minute to conclude your speech.
Yeah, sure. Okay, no worries. Yeah, so I'll just conclude this fault tolerance part because it's important. And basically, we here specify these max restarts that kind of tells us how many times Ray will attempt to revive our actor. And here in this example, we start from 4, so we initialize our value at 4. We increment in this for loop, we get to 9. Of course, then our tasks fail. We catch this exception. But then when we continue this loop, our actor is already revived. And it is revived from its initial state, from which it is being constructed, and the cycle can continue. So this is the example of this fault tolerance. Time for questions.
Actually, I have one question. The nodes that we are talking about, are they located on a single computer, or they can be distributed through the several servers or computers?
They can be distributed across several servers, yes.
And can you please a little bit elaborate how you run those nodes? I mean, you need to manually run your application on different computers, and you need somehow maybe specify the IP addresses of the neighbors, yeah?
So yeah, Ray has these deployment scripts depending on the environment that you are working on. If you are like, so the most convenient one is the Kubernetes. So if you have Kubernetes, Ray does all that. Ray kind of sets up those worker nodes, set up these IPs, and I should have here. So you have this head node, which is kind of the node responsible for main scheduling and auto-scaling, and have those workers. So during the setup, there's Ray setup process, and Ray setup process exposes IP addresses of workers to the head node and establishes communications between head and workers.
I see. Okay, thank you. Do you have a question? Okay, are you familiar with Spark, or
Yeah.
It does? Can you please elaborate if there are the differences between Spark and Ray? As I understand, the Spark should run on the case when your data is very huge, yes, and the Ray cluster may be used in cases when you have a lot of computationals to have. Am I right, or there are other differences?
Yeah, that's an excellent question. So first thing, there's integration with Ray and Spark. So there's Spark Ray that you can use, and it's basically Spark with a Ray cluster. But Ray is kind of more generic. Ray is very useful when you try to train and serve machine learning models. And with Spark it is used for data aggregation and data engineering. And Ray has plenty of integrations with Torch, TensorFlow. There is Horovod, distributed deep learning training framework. They have a lot of integrations with Mars, Spark for data aggregation. So Ray is kind of very generic and has plenty of integrations with these famous frameworks.
Thank you very much for a very interesting presentation. I think there is no question from the auditorium. Yeah, so